Okay, let's unpack this. We're going straight to the core of existence today. Really challenging a fundamental assumption, aren't we? That physics is just about mass and energy.
We really are.
And we're asking maybe the most profound question possible. Is the universe fundamentally conscious?
Which, usually sends people running for the philosophy department.
Right. There's lots of hand-waving.
Exactly. But look, if we're going to be serious about this, if consciousness or even just, let's say, complex information processing is a real feature of the universe, physics needs to account for it. We can't just talk metaphysics.
It needs a term in the equations.
It absolutely does. If the universe has some form of self-awareness, even an emergent one, that awareness must have a physical consequence. It must exert some kind of stress on space-time itself.
Yeah, and traditional general relativity, well, it's always been about geometry telling matter how to move and matter telling geometry how to curve. That's all in the standard stress-energy tensor, right?
Yeah.
Qμν.
Precisely. Qμν covers the stuff we see and measure pressure, density, momentum. The physical stuff.
Gas, stars, radiation.
That's it. But what if the universe is doing more? What if it's processing information, organizing itself, having some kind of informational state? That's completely missing from the standard picture.
Yeah.
Where's the quantum entanglement? That's pure information. How does that affect gravity?
That's the gap.
That's the grand challenge, and it's exactly what this framework we're diving into aims to solve.
So the core thesis for this deep dive, the answer lies in the quantum unified vacuum theorem, the Qμν theorem, basically. And this claims that the universe does have emergent properties, things like consciousness, because it mathematically links space-time geometry, its dynamics, directly to things like entanglement entropy, fractal structure, quantum fluctuations.
It's a fundamental rewrite. We're talking about changing the bedrock of reality here.
Yeah.
Take the classic Einstein field equation.
The one everyone knows, or at least has seen.
Right, and we modify it. We say geometry isn't just responding to classical matter and energy. There's another source term. So the equation becomes, well, it looks familiar at first. Qμν plus lambda, Qμν equals.
The usual constant, 8 pi g over c to the 4th.
Exactly, times. And here's the change, Tμ plus Qμ.
Okay, so Qμ is curvature, Tμ is the normal stuff, and this extra piece, Qμ, this is the entanglement correction tensor. This is where the universe's informational state gets encoded.
That's it, precisely. Qμ. That's the term that makes the vacuum dynamic, active, maybe even self-aware in some sense.
The consciousness term, so to speak?
Well, or at least the informational dynamics term. And the key thing, the power of this synthesis, is that Qμ isn't just pulled out of thin air. It's not an arbitrary fudge factor.
Yeah.
It's constructed piece by piece from quantum information and thermodynamics.
Okay, let's get granular then. If Qμ is representing something as complex as emergent consciousness, it can't be simple. What's it made of? What are the operational components, the mechanisms?
Right, so the Qμ tensor isn't monolithic. It's defined by three physically distinct components. Each represents a crucial aspect of what you might call the universe's self-regulation or awareness, and they all stem from quantum information principles.
Okay, component one, you mentioned self-perception.
That's the alpha term, the curvature energy coupling. Mathematically, it's alpha times Rₘₙ T minus 1/2 Gₘₙ RT.
Okay, let's break that down. Rₘₙ is the Ricci tensor, curvature.
Yep, local curvature, and T is temperature.
Oh, temperature of the vacuum.
Exactly, the thermal state of the vacuum, T thermal. And this is where it connects fundamentally to the Unruh effect.
Yeah.
The idea that if you accelerate through what looks like empty space.
We detect heat, a thermal bath.
Precisely. Acceleration creates temperature locally. So the mechanism here is that the local geometry, the curvature Rₘₙ, is directly coupled to this vacuum temperature. Curvature is related to acceleration, fundamentally. So space-time curving.
It generates heat locally.
It generates a local temperature.
Right.
And here's the feedback loop. In the Qμν framework, this generated temperature then feeds back into the stress energy tensor that shapes the geometry.
Wow. So the universe bends, that creates a local temperature, and that temperature then affects how much it bends.
You got it. It's the universe's capacity for self-perception. It perceives its own shape, its own curvature as a temperature change, and that perception acts as an informational force influencing the curvature itself. It's a closed loop. Geometry and thermodynamics locked together at every point.
That is. Yeah, that's radical. The vacuum isn't passive anymore. It's actively responding thermally.
Right.
Okay, but a conscious system, or even just a complex one, needs more than perception. It needs some kind of drive, maybe towards organization, evolution.
Absolutely. And that's the second component, the entropic gradient stress. We call it the beta term. It's given by beta times K, B times, well, it involves gradients of entropy. nabla mu, s times nabla nu s, minus a trace term, 1/2 g mu nu times nabla squared.
Okay, nabla mu s, the gradient of entanglement entropy. So how rapidly the information disorder changes across space, that directly sources stress and energy.
Exactly that. S here is specifically entanglement entropy, the measure of quantum correlations, the information disorder in the vacuum. This beta term treats the spatial change in that entropy as a dynamic field. Structurally, it looks a bit like the kinetic energy term for a scalar field.
But it's sourced by information differences, not a particle field.
Correct. Purely by the difference in informational organization from one place to another.
So if this represents the drive for organization, does that mean geometry actively resists places where information is messy or changing too fast, like it tries to smooth things out?
That's a perfect way to think about it. It acts to dissipate disorder. It penalizes high entropic gradients. It drives dynamics in an entropic sense. And this is where the cosmology gets really exciting. This beta term is the component that is believed to replace dark matter.
Whoa, okay. Pause there. That's a huge claim. We're throwing out cold dark matter particles.
We're replacing the need for them.
And instead, we're saying there's a thermodynamic force driven by the universe trying to organize its own information.
Yes. Think about it. How does this generate a long-range force? It's similar in spirit to some entropic gravity ideas, but here it's formalized within the full field equations. In regions where normal matter is sparse, like the outskirts of galaxies.
Where dark matter effects dominate.
Right. The entropic gradient term can become relatively important. It imposes a kind of stability constraint on the geometry based on the local information state. And this constraint generates an extra acceleration field. Critically, it drops off more slowly than standard gravity.
Which is exactly what you need to explain flat rotation curve.
Precisely. It mimics the gravitational effects we attribute to dark matter, and it seems to naturally adhere to things like the baryonic-Tully-Fisher relation without needing to invent a new unseen particle. The missing mass problem becomes a missing information organization problem.
That's incredibly elegant, actually. It connects the dark sector directly to information theory. Okay, so we have perception, alpha, and organization, beta. What's the third piece, the sort of underlying layer?
That's the gamma term, the quantum fluctuation stress, mathematically.
Yeah.
Gamma times sigma mu, sigma nu, minus a trace term, 1/2 g mu, sigma alpha, sigma alpha. This is the baseline, the noise floor of reality.
And sigma mu, what does that represent physically?
It comes from the continuum limit of fundamental quantum interactions. Think about the correlation between spins of quantum particles, like qubits. It's related to the expectation value of sigma x dot sigma y in quantum mechanics. Essentially, it's the stress energy contribution for the inherent quantum jitters, the zero-point energy, but defined by its correlational structure.
So the vacuum isn't just empty space that happens to fluctuate. It's an active network, a web of constantly interacting, entangled qubits.
That's the picture.
And the collective stress from all their correlations is baked right into the geometry of spacetime.
Yes. This is the universe's inherent quantum computational noise. It suggests the vacuum is this active informational fabric, constantly communicating its state via entanglement. So the Qμν theorem puts these three layers together: the thermal feedback loop, alpha, the drive for organization, beta, and this fundamental quantum noise, gamma. That's the unified mechanism for emergent cosmic awareness.
Okay, this is a radical modification of GR. So two immediate hurdles, right? First, mathematical consistency. Does it obey conservation laws? You can't just break energy conservation.
Absolutely not. That's the first test any theory like this has to pass. Violate local conservation of energy and momentum, and you're done.
And second, predictive power. Are these constants, alpha, beta, gamma, are they just dials we twiddle to make it fit, or do they come from somewhere fundamental?
Both crucial points.
Right.
Let's take conservation first. The beautiful thing here, the rigorous part, is that the conservation law nabla mu qμ equals 0 isn't an extra assumption we bolt on. It's an unavoidable mathematical consequence of the theory structure itself.
Okay, walk us through that. How does adding this Qμ term guarantee its own conservation?
It comes from the foundation of general relativity itself. Remember the modified equation. Gμ is proportional to the sum Tμ plus Qμ.
Right. Geometry equals matter plus information stress.
Now, the Einstein tensor, Gμ, the geometry side, it must satisfy something called the Bianchi identities. That's just part of the mathematical structure of curved spacetime.
Okay, geometric rules, consistency conditions for curvature.
And those identities mathematically force the divergence of the Einstein tensor to be 0. Always. Nabla mu Qμν is identically zero. Geometry inherently enforces conservation on itself.
I see where this is going, because the left side of the equation, Qμ, is automatically conserved.
The entire right side, the total source Tμ plus Qμ, must also be conserved. Its divergence must also be zero.
So nabla mu of Tμ plus Qμ equals 0.
Correct. Now, we already know that standard matter and energy, Tμ, is conserved on its own. Nabla mu Tμ equals 0. That's a cornerstone of physics.
So if the total is conserved, and the Tμ part is conserved, then the remaining part, the Qμ term, must also be conserved. Nabla mu Qμ equals 0. It's not an assumption, it's demanded by the underlying geometry of GR. The consistency of space-time itself requires the informational stress energy to be conserved.
That's incredibly neat. It moves it from just an interesting idea to something mathematically sound. Okay, rigor check passed. Now, the constants. Alpha, beta, gamma, where do they come from? Starting with alpha, the curvature energy coupling.
This derivation is really a beautiful piece of work, blending quantum gravity ideas with thermodynamics. We get the value of alpha by basically matching the energy scale. We look at the energy density implied by the Qμ term, specifically the alpha term, in a theoretical universe called a de Sitter vacuum.
Okay, an empty expanding universe model. Why there? Because a de Sitter vacuum has a cosmological horizon, much like a black hole horizon. And these horizons have thermodynamic properties, temperature, entropy. The alpha term links curvature to temperature via the Unruh effect. So we demand consistency. We say the energy density coming from this curvature-temperature coupling in the de Sitter space must match the energy density you'd expect from a thermal bath, like blackbody radiation, at the Unruh temperature associated with that horizon.
So you're forcing the information-driven energy to be consistent with the known thermodynamics of space-time horizons.
Exactly. It connects the geometric entropy, like Bekenstein-Hawking entropy, with the thermal energy inherent in the vacuum due to its structure and expansion. It's a fundamental calibration point.
And this calculation gives a specific number.
It does. It involves fundamental constants, Planck's constant, speed of light, Newton's g, and also includes a factor involving the Riemann zeta function, zeta of 3, which often pops up in thermal quantum field theory calculations. The result is alpha is approximately 1.72 times 10 to the 67 Kelvin squared.
That's a huge number.
It is. It emphasizes just how sensitive the geometry is to thermal perturbations, even tiny ones from quantum effects. It shows the strength of this self-perception mechanism.
Okay, so alpha is grounded in thermodynamics, but the sources claim something even more astonishing, that this framework derives the fine structure constant, alpha EM, the strength of electromagnetism. How does a theory about gravity and information predict that?
This is where it potentially bridges the gap to particle physics through geometry. The core idea here is that the fundamental strength of the electromagnetic force alpha EM, about 1 over 137, isn't just some arbitrary number. It's determined by the fractal dimension of the vacuum itself, which we call d sub f.
Fractals. Okay, that implies self-similarity, patterns repeating at different scales, a holographic feel.
Absolutely. The theory suggests the universe's informational structure isn't smooth, but fractal. It calculates a specific value for this dimension. d sub f equals log 8 over log 3, which is about 1.8928. This number characterizes how densely information is packed into the geometry, how it flows.
So d sub f is like the operating system's spec for information handling. How does that give you alpha EM?
The derived relationship is alpha EM equals 2 pi over the natural log of 10 times 1 over d sub f raised to the power EM. There's a slight modification for the electromagnetic dimension specifically, but the key insight is this. The strength of a force like electromagnetism is essentially determined by how easily information, in this case photons, charge interactions, can propagate and interact within this fractal network. The calculation shows that the stability of atoms, the strength of chemical bonds, is literally rooted in the information flow properties of spacetime's fractal structure.
That's mind-blowing. The force holding us together is a consequence of the universe's informational geometry. And the last constant, gamma, the quantum noise term.
Yes, a gamma constant. Its derived value is about 7.297 times 10 to the minus 3. Numerically, that's extremely close to alpha EM.
Almost identical.
And the theory argues this is no coincidence. It suggests a deep unification. The strength of the underlying quantum computational noise, the gamma term, and the strength of electromagnetism, alpha EM, are intrinsically linked. They both depend on this same fundamental fractal dimension of the vacuum. The physical interactions in the quantum noise floor are two aspects of the same underlying geometric information structure.
Okay, we've got a conserved theory, derived constants grounded in fractals and thermodynamics. But if the universe is this information network, does it look the same up close as it does far away? How does this handle the huge scale difference between quantum stuff and cosmic gravity?
That's where scale dependence comes in. This is maybe the most innovative cosmological aspect of the Qμ theory. The coupling constant alpha, the self-perception term, isn't actually constant. It runs. It changes with energy scale, K, and also with cosmic time, or redshift, Z. So we write it as alpha of K.
That's a big departure. G, the gravitational constant in GR, is, well, constant. Why would the universe's self-perception change with scale?
It seems it has to, if you want to bridge the gap between the quantum and the classical and solve some big cosmological puzzles at the same time. Look at the form it takes. Alpha of K, Z equals alpha 0 divided by 1 plus K over K star of Z squared.
Okay, so K is the energy scale or momentum scale. What happens at large distances, low energy? Small k.
Right, the IR limit, infrared. As K goes to 0, that second term in the denominator vanishes. Alpha of KZ just becomes the constant alpha 0 we derived earlier.
So at large scales, the quantum correction, the Qμ term's influence v alpha, fades away.
Almost entirely. And you recover standard general relativity. That's crucial. It ensures the theory matches all the tests we've done in the solar system with large galaxy surveys and so on.
Okay. But what about high energy, small scales? Large K, the UV limit.
Then the denominator gets large, alpha K's gets suppressed, but the Qμ term itself becomes dominant relative to Tμ. The universe's informational structure starts actively dictating the geometry near the Planck scale.
It's like the universe has different operating modes depending on the resolution you're probing it at. A holographic self-image.
That's a good way to put it. The physical laws we see emerge from these deeper informational rules, but the effects are most obvious at high energies or small scales, and this scale dependence. This is the key to resolving the Hubble tension.
Wait, how does a theory about consciousness and information fix a mismatch in measurements of the universe's expansion rate? That seems like a totally different problem.
It seems different, but the tension arises because we're measuring the expansion rate using different methods that probe different scales and epochs. Early universe probes, like the cosmic microwave background, the CMB, they're looking at physics when structures were small, when these scale-dependent Qμ effects for alpha carry Sol would have been more significant. They give a lower value for the Hubble constant, H0, around 67 kilometers per second per megaparsec.
Right, and then late-time probes like supernovae or large galaxy surveys like DSI, they look at more recent, larger structures.
And they consistently get a higher value, around 73. The discrepancy is statistically significant. It's a real tension.
They're measuring the universe at different zoom levels, effectively.
Exactly. And the Qμ theory says, well, gravity itself behaves differently at those different zoom levels because alpha runs with scale. Specifically, it modifies how structure grows over cosmic time. It tends to suppress structure growth slightly more at the smaller scales relevant to the early universe, affecting things like CMB lensing calculations.
Ah, so if the model changes how structure grows, it changes how we interpret the CMB data to infer distances and the expansion rate.
That's the crux of it. When you plug the running alpha KAZ into the standard cosmological model, it naturally resolves the discrepancy between the early and late universe measurements. The theory predicts a single value for the Hubble constant. H0 is about 68.2 kilometers MPC.
Which is right in the middle. And it lines up incredibly well with recent large-scale structure results like DSI, which reported something like 68.5 plus or minus 0.8.
The alignment is remarkable. It suggests the Hubble tension wasn't a crisis, but actually a clue. A hint that gravity itself isn't scale independent, that the universe's informational nature matters.
It's the universe showing us its underlying fractal scale-dependent structure. And you're saying the same principle, this information flow affecting geometry, works down at galactic scales too, reinforcing the dark matter replacement.
Yes, absolutely. We need to connect back to the beta term, the entropic stress, and its role in galaxies. This is maybe the most direct macroscopic test.
Right, the claim that entropic forces replace dark matter particles, how does that play out with the scale dependence?
When you combine the entropic gradient stress, the beta term, with this overall scale-dependent framework from the running alpha, you get a modification of gravity that very precisely describes how matter moves inside galaxies. Think about the baryonic Tully-Fisher relation again.
The tight link between a galaxy's visible mass, stars and gas, and how fast its edges rotate.
Exactly. Standard dark matter models need to carefully tune the distribution of dark matter, the halo profile, to match that observed relation. It works, but it feels a bit engineered.
Okay, how does Qμ do it?
The entropic force, driven by the beta term, naturally becomes significant in the low acceleration regions, the outer parts of galaxies, precisely where we invoke dark matter. This thermodynamic force, which represents the universe locally trying to minimize information gradients, trying to organize itself, it generates an extra gravitational pull that mimics dark matter. And crucially, because its origin is tied to these fundamental thermodynamic and informational principles, it naturally follows the specific scaling observed in the Tully-Fisher relation without needing arbitrary tuning.
So it unifies the large-scale puzzle, maybe related to dark energy through the running alpha, with the small-scale puzzle of dark matter through the entropic beta term.
That's the power of the synthesis. It proposes one coherent, information-based thermodynamic framework that addresses both dark sector problems simultaneously.
Okay, mathematical consistency is there, cosmological coherence seems promising, but this is physics. We need empirical proof, hard evidence. What are the definitive testable signatures of this Qμ entanglement network? Where can we actually see cosmic thought, or at least its effects?
We need experimental benchmarks. The theory offers two major predictive pillars that are, at least in principle, testable. First, looking at the most extreme gravity, the black hole remnant. Think of it as the universe's memory core.
Okay, standard GR says black holes have singularities, points of infinite density, and they destroy information via Hawking radiation, the information paradox.
Right. But Qμ changes that picture dramatically because the entanglement correction tensor, Qμ, includes terms that become strongly repulsive at incredibly high densities, near the Planck-scale.
Like the quantum fluctuation stress.
Exactly. It prevents gravity from crushing matter all the way down to an infinite point. The gravitational collapse halts. Instead of a singularity, you get a stable, zero-temperature object, a black hole remnant, or BHR. It has a finite density, a structure.
So it's not a point, it's a tiny stable nugget of Planck density stuff. And because it's stable, it preserves the quantum information that fell in.
Precisely. It resolves the singularity and the information paradox in one go. The information isn't lost, it's stored in the structure of the remnant.
A cosmic hard drive.
In a manner of speaking. And the theory gives a very specific prediction for its mass. The remnant mass, M remnant, is directly linked back to that fundamental fractal dimension, d sub f. It predicts M remnant equals the Planck mass divided by the square root of d sub s.
Okay, Planck mass is tiny, about a microgram, and d sub f was about 1.89. So the remnant mass is even smaller, about 0.726 times the Planck mass. That's incredibly specific. But how on earth do you observe something that small and dense?
You don't see the remnant itself directly. You look for its influence on big astrophysical events, specifically the gravitational waves from merging black holes. After two black holes merge, the final larger black hole settles down. It rings down, emitting gravitational waves.
That's the signal LIGO, Virgo, Qₘₙ detect, the characteristic chirp, and then the ring down.
Exactly. Now, because the Qμ theory predicts the final object isn't a classical GR black hole with a singularity, but contains this quantum remnant structure inside, it should affect the ring-down signal. The prediction is that we should see subtle secondary oscillations, maybe described as a modulation envelope, appearing in the late part of the ring-down signal. Not immediately after the merger, but perhaps days or even weeks later, as the remnant structure subtly interacts with the surrounding geometry.
Like an echo.
Sort of, yes. A quantum echo imprinted on the gravitational waves. Finding these specific secondary modes, especially in a high signal-to-noise merger event like, say, GW250114, which is mentioned as a potential candidate, would be the smoking gun. Direct evidence for the quantum structure inside black holes predicted by Qμ.
A direct link from Planck-scale physics to billion-light-year astronomical observations. Okay, that's one pillar. What's the second? Can we test this in the lab?
The second pillar aims to do just that. It focuses on testing the alpha term, the curvature energy coupling, directly. The enhanced Unruh effect. This probes the universe's self-perception mechanism.
Right, the idea that acceleration creates temperature, linked via the alpha constant.
If that link is real, we should be able to measure it. The Qμ theory predicts that the standard Unruh temperature formula, T Unruh, equals h bar times acceleration over 2 pi ckb, is actually incomplete. It gets modified, enhanced, by this geometric coupling encoded in alpha. Because local temperature and local curvature are tied together, the overall thermal effect of acceleration should be stronger than predicted by standard quantum field theory in curved spacetime.
And this enhancement, it's big enough to potentially measure.
That's the key prediction. It suggests it is. Experiments like LUXE at DESY, which use incredibly powerful lasers to accelerate electrons to extreme levels, are pushing into the right regime to potentially see this. The Qμν theory predicts that the ratio of detected unruh photons to, say, background Compton scattered photons should be significantly higher, potentially by more than 2 orders of magnitude compared to baseline predictions.
So it lifts the signal out of the noise.
Yeah.
Makes it potentially detectable.
That's the hope. If LUXE or a similar experiment detected such an enhancement, it would be strong evidence for this fundamental coupling between geometry and vacuum temperature, the alpha terms mechanism.
Okay, detecting the remnant echo or the enhanced unruh effect would be huge. But you mentioned a critical benchmark earlier, the causal structure.
Yes, this is maybe the most fundamental test, philosophically and physically. The whole premise of this framework is that geometry, space-time itself, emerges from a deeper layer of quantum information and entanglement.
Information comes first.
Information comes first. Gravity is the result, not the cause. Therefore, the causal order is absolutely critical. To truly validate this, we would need experiments or observations, maybe using cosmological correlations or future gravitational wave data that can perform a cross-correlation analysis. We need to show, statistically, that changes in entanglement entropy precede changes in spacetime curvature.
So you'd need to see the information state changing slightly before the geometry responds, not the other way around.
Exactly. There must be a demonstrable lag, even if it's incredibly tiny, maybe on Planck timescales. The information state must be shown to drive the geometric changes. If we found curvature changes cause entanglement changes, then this whole emergent picture falls apart. Proving that causal order information first, then space-time is the ultimate hurdle for confirming the universe isn't just processing information, but that information is what reality is.
So wrapping this up, what does it all mean? If this Qμν theorem holds up, it's not just a tweak to gravity. It feels like a complete paradigm shift.
It really is. It's grounding physics in information.
It replaces the idea of a passive, empty vacuum with this dynamic, self-referential quantum network. And consciousness, at least in this physical context, isn't some spooky extra thing. It's the universe's ongoing process of turning entanglement, pure information, into geometry, into physical reality, driven by principles like entropy.
Exactly. It fundamentally reframes causality in existence. And because it makes these concrete predictions deriving constants from thermodynamics and fractals, potentially explaining galactic rotation, the Hubble tension, predicting black hole remnant signatures, enhanced unrow effects, it moves beyond just being a compelling philosophy. It becomes testable physics. The universe isn't just following laws written down somewhere. It's actively writing those laws through its own process of self-entanglement, using its information structure to define its own constants and dynamics.
It takes the weirdest parts of quantum mechanics, like non-locality,
Uh-huh.
and says they aren't weird glitches. They're the foundation. They're why space-time exists.
Precisely. The Qμν theorem offers a new perspective on things like the EPR paradox, the spooky action at a distance. It suggests it's not spooky action across distance, because distance itself might not be the fundamental thing. Instead, entanglement, these non-local correlations, might be the very mechanism that generates the geometry, the connection we perceive as distance. It replaces spooky action at a distance with something maybe even more profound. Geometrical connection without fundamental distance. Wow. So the final provocative thought this leaves us with, if the universe is driven by these informational dynamics, conserved and entropy-driven, is the emergence of life, of biological consciousness like ours, just another, perhaps more complex, manifestation of the same fundamental organizational drive that shapes galaxies? That's the deep question, isn't it? It forces you to ask whether the consciousness we find here on Earth is truly separate from the underlying informational processes of the cosmos itself, or if it's just a particularly intricate ripple in that universal awareness.